I'm going to describe some research which is fairly new for me. My background, as many people who I know well in this room will know, is really in neuroimaging. I'm trained in clinical psychology, but I've been more on the biomarker side through most of my career. But over the last really very short period of time, about 10 months, I became very interested in how we can use technology to better understand a couple of issues that were nicely brought up in the prior talks. One is the heterogeneity of autism, and two is how do we enable our studies to be larger so that we have larger sample sizes so that we don't have replication errors. So there's a famous paper from 2005 by a Stanford scientist who wrote, and this was shocking at the time, it's more likely for a research claim to be false than true. 10 years of study of this phenomena since then has largely bore that out, that lots of research doesn't replicate. The main reason, it turns out, and this is a good thing because it's addressable, is sample size. The human condition is just too variable when we have a small sample and think we're representing the whole population, which is what we do with a sample. It just doesn't. And so the study is correct for the sample, but it's not generalizable for the whole society. I think that the tools I'm going to show you today are going to be valuable because they allow us to measure behaviors in a very precise and quantitative way, and they can be deployed in the real world, which really will allow us to have larger samples. The second thing that makes me super excited about this work is that it's now possible with advances largely in computer vision, less so in the hardware, to digitize and analyze everything that an expert clinician can observe. So expert clinicians, when they're evaluating someone, or you at a cocktail party when you're evaluating someone, you're paying attention to features like the affective tone of the voice or the prosody or other acoustic features. If a child has autism, you might be looking for things like abnormal motor movements, repetitive behaviors. You'll also pay attention to the language, the words that kids use as a window into their mind. What are their special interests? Are they preoccupations? We've done some research where we found that the frequency of word use in kids with autism is different than kids without autism, and that becomes a feature. I'm going to use the word feature quite a bit in this talk because the analysis platform we use behind this is known as machine learning, and you look at features in that. But to the core of autism, this video analysis technique is also going to allow us to look at nonverbal communications. So we can quantify facial expressions, we can quantify eye contact, we can quantify the use of gesture. And most importantly for us, and this is where we started, we can quantify the dyad, the relationship between people who are communicating. So it's very early days. I'm surprised I'm standing here after only doing this for 10 months, but I think it's exciting to those who have seen it. I think the first step is to use this information to predict who has autism, and we've started off with the easiest case. These are people who already have autism. But eventually we're going to get at the issue that Wendy raised, and I think Jamie touched on, which is what is the essence of autism? Is it a categorical structure? Is it a set of underlying latent traits? To do that, you need lots of data, and the techniques I'm going to describe today give us lots of data. So if you could click that movie, please, Jay. So this is a little boy who's 2 years old. His name is Ali. He's the son of a psychologist who works with us. He walked into our lab, which was a special lab. You can see up top in the upper right, there's a bunch of little squares. Those are cameras. They're not special cameras. In fact, those cameras are $7 a piece. So the hardware is not that special. He has nothing on. If this were Hollywood and we were making a film like Shrek, he'd have some sort of reflective markers. He just walked in. The computer vision has gotten so good now that we can estimate where his bones and joints are, and we can superimpose it. And that gives us a four-dimensional cloud of data that we can analyze. What I didn't appreciate a couple years ago as someone who was studying the perceptual side of autism, that motor symptoms are very pervasive in individuals with autism. And the effect sizes, or the degree to which these features can separate individuals with autism from healthy controls is big. And so we're following the effect size as we begin to measure these things. You could look at symmetries. Is the left and right arm going together? The idea is to get a large database, say 5,000 individuals, and have it denormative. And any child that came in and begins interacting or moving, we can say, how typical is that in an actuarial sense? So we can also do things like find out what was the direction of the path. Was there proximity seeking? Was there social approach? What was the nature of the exploratory behavior? On the left side here, you see what traditional psychologists were doing just 4 years ago in 2012, which was enormously labor intensive. And we get that information for free by having a child walk into the room. It's also true that things like imitation to command, do what I'm doing, is an area of great weakness for kids with autism. They don't do it well, and again, the effect sizes here are large. And here what you can see is, again, that same room you saw before, but now there's a table in it, and there's a research assistant and a young adult who's participating in the study, and they're just simply asked to do an arm movement. And you can map out precisely in XYZ coordinates the exact movement of that arm. And again, use that quantitatively. It might be the differences are so subtle that the human eye is not going to capture it, but the computer will. The advantages of the computer is it never has lapses of attention, and it never forgets. So you have all that data. This is another demonstration of measuring imitation. One of our research assistants moved his arms, and that's a video, and the person's looking at it. This could be done at home. We're actually in conversations with cable providers. Can we push this to TVs and have people do this at home and actually measure this in the real world on a very frequent basis? And below is just the plot of the movement across time. You can see how those two look alike, but they don't map exactly the same way. We're also interested in motor learning. I work with a really smart undergraduate at Penn named Allison Langer, who's actually a dancer. So she created, if you could hit that start, please, Jay. She's a dancer, so we're asking how well do kids with autism learn dance movements? What is the rate of learning? There she goes. And so she's demonstrating some basic dance moves that were, before this movie, taken and taught in an individual manner. Up top right is her skeleton, and down below is a participant, an adult participant with autism trying to copy those. So this is a more complex thing. Her interest in this stems from her interest in herding behavior and schooling behavior. These are very conserved principles of synchrony between individuals of the same species. So an underlying theme of what we're interested in is this idea of motor synchrony. Can it go into the wild? Can it go into the community? It can, and we proved that last summer. So on the left there, I'm showing 2 cameras. They're called Connect cameras, a laptop and a milk crate. And we took that around to summer camps, and we set it up. We can take it around to schools and JCCs and YMCAs, which we're doing. And we can measure it where the kids are. I think I can control this one. Okay, this is Keith, who's a brilliant computer scientist with our group, and he's sitting in front of a laptop, and he's making facial expressions. On the right is the representation of those facial expressions. By the fact that we can represent it means we're measuring it. We have a very dense grid of data on top of his face, and we can very precisely look at how is he moving. What is the symmetry between left and right? What is the relationship between eyes and mouth? This is Keith moving again, but this time we're focusing on his eyes. As you all know, I'm sure, the direction of eye gaze, eye contact is a critical marker for kids who have a social disability. I've done a lot of screen-based eye tracking myself, but the holy grail, to borrow a Wendy term, is really, can you do it in the real world? Can you do it? And we're showing that you can with this. There's still some math and details to work out, so I'm not saying we've done it in the 10 months, but you can see just from the eye movements that it's completely feasible to understand what is the direction of eye gaze in a real-world setting. Okay. To do this, we had to build some equipment. We really are interested in that conversation between 2 people, so we had to build a special dyadic camera. This is demonstrating the 3rd generation of that camera on the middle of the table there. We call it our tree cam. It can hold more than 40 hours of data. It has a plug, but it also has a battery. It can sit there for 6 hours and record. So it's a good way to get synchronized data, and for the analysis, it has to be synchronized between the individual with autism and whoever they're talking to. And if you could hit that, Jay. This is an example of that kind of data. Again, Keith, this time with his daughter, Brianna. They're down on vacation. Over Keith's shoulder, you'll notice sand and water. They're at the beach, so they're in a natural environment. It doesn't need to be that loud. And what we're showing is one of the readouts. In this time, it's eye direction of gaze. And at one point, Keith is recording this for me because I asked him to, he's nervous, and he looks to the left or to the right, and she follows. And you get a very precise definition of how long did he look away, what was the phase lag in her eye gaze. That also might be a feature which surprisingly could be very predictive of autism. All these features have never been available, so we wouldn't have the depth of understanding that we might be able to gain from this information. We wanted to know if we could predict people who already have autism. So we did an adult study. We looked at 44 individuals, 17 with autism, 17 controls. They were matched on these relevant variables. We used our tree camera. They sat and they spoke to each other for 3 minutes. It was a very unstructured conversation. It was like, sit down, get to know each other, I'll be back. And we wanted to know, were there movements that individuals with autism had that we could then categorize blindly who has autism and who doesn't. And we were surprised because it's 3 minutes. I think you need to start this one too, Jay. Up top, I'm showing a plot. Again, this is two people talking in that 3-minute conversation. Up top, I'm showing a plot of different features that we decided to put on that plot. There's many more, but head pose, eye movement, eye blink, etc. And the red bar for each person is their average movement across the entire 3 minutes. And there's two people talking. We can get a precise interaction at the feature level of two people talking, and we can fully cross it. We can fully cross those features and ask, in a time-lagged way, when the woman on the right, who's a research assistant, makes any kind of movement, can we understand the movements a second, 2 seconds, 3 seconds later in the person with autism? That's kind of a predictive causality. And will the synchrony, the feature that we use is known as mutual information. If I can predict what the man on the right is doing from the woman's behavior on the left, then there's a degree of coherence to their motions, and we can measure that through this mutual information metric. Okay, so we did that in these 44 individuals. And what really surprised us was how easy it was to figure out who has autism. We were 90% accurate in this group of 44 of saying who had autism and who didn't, from the synchronous behavior across a 3-minute conversation, which was highly unstructured. We are targeting these brief kind of paradigms because we want to put this in schools. We want to put it in primary care. There are 10,183 kids at CHOP last year who came into primary care. Can we get a nurse to have a 3-minute conversation that could be put into the medical record? We're showing one of those features up here. They're named P13 and P4, and there's a time lag. But when the woman on the right, who's the research assistant, makes a certain facial movement, the guy on the left nods. And that nodding in this example turned out to be one of the very predictive features. And I'll show you one more if I can move it. Okay, this is another feature that was predictive in that model. In this case, the woman on the right is engaged in almost some rocking behavior, and she leans forward. And that was atypical. That didn't happen very often in we had the typically developing adults as well. It's not that noticeable, but the computer picks it up and says, this is distinguishing the groups. I should say that the individuals with autism in this study were mild to moderate. So the fact that we can pick that up in a not severely frank autism group is kind of amazing. Okay, so I think there's a lot of promises to this with the caveat that we're 10 months into it. I think it can allow, we need to figure out how to downward extension, earlier diagnoses and interventions. It can be put into the home so we can get big data. It can reduce wait lists. You know, most places have 9-month wait lists. Can we triage people? Can we screen? Can we make a decision? You know, Johnny doesn't need to see the best, most expert autism expert. They just need to see a nurse practitioner because their needs are so clearly, lesser than someone else. Can it shorten the in-person evaluations? Our in-person evaluations tend to be very long. Can we have a digital assistant before and during that augments that? We'd love to get these into large genetic studies where we can really get much more information about the underlying latent traits that might define individuals with autism. And I also think we should get it into treatment studies. Many of you may have seen a nice article in The Atlantic a month or two ago called The Flaws of Designs of Drug Trials for Autism. The bottom line is there that our outcome measures are not very good. Oftentimes we have treatment trials which we think we really could have seen an effect if we had used the right tool, but our tools are insufficient. One of the things we use are questionnaires, and you can't easily repeat those many times. Cameras and such can be put in the home and could be collected at any frequency. You can't repeat the questionnaires a lot because you get practice effects. How you can fill that out changes by the number of times you fill it out. So I will stop there, and I thank you for your attention.